Welcome to the Rani Chennamma University, Belgavi, BSc 4th Sem Physics Interference, Session 9. In Session 9, we are going to solve some problems on interference. The learning objective of this session is to understand and to solve problems on Fresnel's biprism experiment and also on the constructive and destructive interference in case of thin films. So we need some prerequisites. The Fresnel biprism experiment theory, then Stokes treatment of reflection and transmission at interface, and also the condition for maxima and minima in case of thin films. Let us see some formulae used in Fresnel's biprism. Wavelength of monochromatic source of light is calculated with the help of the equation lambda is equal to beta small t divided by capital D. And then the to determination of beta is equal to xn minus x naught divided by n, and to determination of the distance between two virtual slits uh, is equal to square root of d1 d2, where d1 is the distance between two magnified images and d2 is the distance between two diminished virtual images. Let us see the Stokes law. When the light wave is reflected at the surface of optically denser medium, it suffers a phase change of pi or a path difference of lambda by 2, but there is no phase change takes place when it is reflected from surface of the rarer medium. So we have to add, if the reflection is takes place uh, from the denser medium, we have to add the path difference of lambda by 2. Then the condition for maxima and minima in case of reflected light of thin films. Condition for maxima, that is 2 mu t cos r is equal to 2n plus 1 lambda by 2. And condition for minima is 2 mu t cos r equal to n lambda. And in case of transmitted light, so the formula just opposite that we have studied in reflected light. So the condition for maxima in case of transmitted light is 2 mu t cos r equal to n lambda, and condition for minima is 2 mu t cos r equal to 2n plus 1 lambda by 2. Let us see the examples. In biprism experiment, the eyepiece is at a distance of 120 centimeters from the source. The distance between the virtual sources is 0.075 centimeters. If the fringe width is 0.096 centimeter, find the wavelength of the light source. So here, if the distance between the virtual sources d is equal to the given thing is a 0.075 centimeter, and then the capital D is the distance between eyepiece and the biprism is 120 centimeter. In terms of meter, it is 1.2 meter, and they have given the fringe width, that is beta is equal to 0.096 centimeter. So then convert all centimeters into a meter just by multiplying into 10 raised to minus 2. Okay, and then as beta is equal to lambda d by d, and this lambda is equal to beta into small d divided by capital D. After substituting all the values of beta, small d and capital D, and we get the value of this wavelength of monochromatic light is 6 into 10 to the power minus 7 meter, that is 6000 angstrom unit. Now, see the example 2. A biprism is placed at a distance of 5 centimeter in front of a narrow slit illuminated by sodium light of wavelength 5890 into 10 to the power 8 centimeter, and the distance between the virtual sources is found to be 0.05 centimeter. Find the width of the fringe observed in an eyepiece placed at a distance of 75 centimeter from the prism. So here let us write first the given things. As they have given the wavelength lambda is equal to 5890 into 10 to the power minus 8, that is minus 8 centimeter, and d is equal to this is 0.05 centimeter, and then here capital D is it is the sum of the distance between the biprism to the slit. So it is sum of the eyepiece is placed at a distance of 75 centimeters. So the capital D is equal to 5 plus 75. It is 80 centimeter. And now let us take this beta is equal to lambda d divided by d. This is 5890 into 10 to the power 8. After substituting all the given values, we get the beta is equal to 9.424 into 10 to the power minus 2 centimeter. Now, in a biprism experiment, interference fringes are produced in the focal plane of the eyepiece at a distance of 1 meter from the slit. A convex lens introduced between the biprism and the eyepiece produces two sharp and well-defined images of the slit 6.8 into 10 to the power minus 3 meter apart in one position and 1.7 into 10 to the power minus 3 meter in another. Then calculate the fringe width. If the wavelength of the light used is 588.2 nanometer. So first you write the given things as the D, that is capital D, is equal to 1 meter and lambda is equal to 5808.2 nanometer. So nano it is 10 raised to minus 9 meter. Then the magnified image say D1 equal to 6.8 into 10 to the power minus 3 meter and D2 is equal to 1.7 into 10 to the power minus 3 meter. So as the expression of D is equal to square root of D1 into D2. So after substituting D1 and D2, it is 6.8 into 10 to the power minus 3 into 1.7 into 10 to the power minus 3 is equal to 3.4 into 10 to the power minus 3 meter. And then fringe width beta is equal to lambda d by d. So after substituting the lambda and capital D by small d, as it is 588.2 into 10 to the power minus 9 divided by 3.4 into 10 to the power minus 3 and is equal to 173, that is into 10 raised to minus 6, and this is equal to, in terms of millimeter, it is 0.173 meter. And now the example 4. And two sources of a light are used in a Fresnel biprism experiment. In turn, their wavelength are 5400 into 10 to the power minus 10 meter and 6050 into 10 to the power minus 10 meter. And if the distance between the two virtual sources D is equal to 2.5 mm, then D capital D is equal to 1.2 m. Find the difference between the width of the fringes. So here the fringe width we have to calculate between the two sources, as a lambda 1 is equal to this, lambda 2 is equal to this, corresponding small d is equal to 2.5 mm and capital D is equal to 1.2 mm. Then beta 1 is equal to this much and beta 2 is equal to this much. So if you subtract these beta 1 minus beta 2 corresponding to this one, we get lambda 2 minus lambda 1 d divided by d. So after substituting this, we get the difference in the fringe width is 0.0725 mm. Let us see the example 5. In a biprism experiment, the eyepiece was placed at a distance of 120 centimeter from the source. The distance between the two virtual sources was found to be 0.075 centimeter. Find the wavelength of the light of source if the eyepiece has to be moved through a distance of 1.888 centimeter for fringes to cross the field of view. So here it is having a n is equal to 20 fringes, as the length of the 20 fringes is equal to 1.888 centimeter. Then fringe width equal to beta is equal to L by N, and this is equal to 1.888 divided by 20. So it is becomes a 0.0944 centimeter. So if we know the value of d, small d is equal to 0.075 and capital D is 120 centimeter, then lambda is equal to beta d divided by capital D. And then after substituting the value of beta, that is 0.0944 into 10 to the power into 0.075 divided by 120 is equal to, so the after simplification we get the 59 into 10 raised to minus 6 centimeter. Okay, so in terms of minus 6 centimeter, and this is in terms of in meter. Okay, let us see the next problem. So here in a biprism experiment, the eyepiece was placed at a distance of 120 centimeter from the source. The distance between the two virtual sources was found to be 0.07 centimeter. Find the wavelength of the light of source if the eyepiece has to be moved through a distance 2.0 centimeter for the fringes to cross of the field of view. So as solve in the last solved the same problem. So likewise you have to solve it. The answer is 5833 angstrom. Let us see the problem on thin films. Find the thickness of the soap film, that is mu is equal to 1.3, which gives a constructive second order interference pattern with lambda is equal to 700 nm, and assume the normal incidence. So at normal incidence R is equal to 0. So therefore the here it is a constructive interference. So for the constructive interference, the condition is 2 mu cos R is equal to 2n minus 1 lambda by 2. Say this is equation 1. For a normal incidence, I is equal to 0, and this R is also is equal to 0. So therefore cos R equal to 1, and for a second order it is equal to n equal to 2, and therefore the equation 1 becomes 2 mu t is equal to 2 into 2 minus 1 into lambda by 2. So after substituting this, t is equal to 3 by 4 lambda by mu. As a given things, lambda is equal to 700 nanometer and mu is equal to 1.3. After substituting the values of these, we get the thickness equal to 403.8 nanometer. And this is the one problem that you have to solve it. As a glass slab mu is equal to 1.5 is to be coated with a film of some transparent material of the refractive index mu is equal to 1.25. What should be the thickness of the film at the yellow light, so which is having the wavelength 6000 angstrom, incident normally on the film and is not reflected? The answer is 2n minus 1, 1200 angstrom. So here we solved problems on the Fresnel biprism and thin films. These are the references you can refer. Thank you.